to be our fourth talk this year. So if you missed any of it, go to our YouTube channel. And as usual, we're recording the talk part, but not the Q&A. And so Ramana, you can go ahead and introduce a speaker.
Yeah, today we have Dr. Jin Xiao, who is currently a tenure track faculty at the University of Science and Technology of China. He obtained his PhD from Georgia Tech in the US. He then went to University of Iowa for his postdoctoral research. And prior to his current employment, he worked sequentially at the Laboratory for Atmospheric and Space Physics, or LASP, at the University of Colorado Boulder, and at the Dublin Institute of Advanced Studies in Ireland. His research spans a broad range of space physics topics, including Earth's ionosphere and magnetosphere, as well as magnetospheric and atmospheric environments of giant planets and icy moons. He has extensive expertise in instrumental data analysis, MHD numerical simulations, and artificial intelligence assisted modeling for space physics research. And that last part is what we're going to hear about today. So, Dr. Xiao, please take it away.
Uh, Thank you for your introduction, Ramana. So today I'm going to talk about my research about the neural network-based ionospheric current prediction with focal logs for imbalanced data. So basically, this work has already been done by me and my collaborators who are working in LASP and UCLA as well. And first of all, let me just briefly introduce what is a GIC. So basically GIC is geomagnetically induced currents. Somebody might be familiar with it. So basically the GIC is created by the rapid fluctuations of magnetic fields through a process called electromagnetic induction. These fluctuations can be ultimately driven by the interaction between the solar wind and Earth's magnetosphere, causing events such as geomagnetic storm and substorms, and impact ground-based infrastructures such as like the railroad tracks and the underground pipeline, power grids, something like that. In the ionosphere, we're basically in lack of direct measurement of the GICs. However, we can use a method. It's called like spheric elementary current system method to derive the equivalent ionospheric current, which is called EIC, from the ground based magnetic field disturbance. Therefore, we can have a look at the EIC as a proxy of the GIC in the ionosphere. Understanding how EIC develop in response to external drivers such as the magnetospheric indices can provide us key information that describe the variation of the GICs. And this is an example to show the EIC-derived observations in the North American and Canadian sector during a substorm event occurred at 2008, February 29th. In the contour map here, in the right-hand side, the red color shows a significant westward electrojet within the mid and high latitude region. Prediction of the variations of the EIC is important for us to understand its response to the external physical drivers. So we used the feedforward neural network to predict the EIC's response to the external drivers. Here, we show the structure of our neural network model. There are 3 layers in total, and the number of nodes in each layer are shown in the right-hand side. The input parameter include like something like AU, AL, CMAG, and F10.7 indices, and their time-delayed moving average values, which indicate the current and historic fluctuations. We also include the location information of the EIC's occurrence, such as the sine and cosine latitude and the longitude and the local time. The output of the model is EIC JY component, which indicate the westward or either westward or eastward electrojet, which depends on the value, the sign of the values. In the initial setup of the model, we used MSE as the loss function to be optimized, which must be very familiar with all of you. So these are the initial results for our MSE loss function model. The left side shows the model observation comparison. 4 different panels shows the whole data set, the training, validation, and testing data sets respectively. And we can see that the most of the model predictions are not aligned along the diagonal line y equals to x, which stands for a good match with the observations. And the right-hand side shows the error distribution of the predicted EIC versus different local times. So here, we just further choose 2 different substorm events to show our initial prediction by this MSE loss function model. The first 2 panels show the AU, AL, and SIMH indices. The following 4 panels are kilograms and EUgrams for a comparison between the observations and our model, our MSE model, basically. We can see that this model can predict the occurring time of the westward electrojet reasonably well, so which indicate by the red colors. But if we look at the last panel, well, which shows the mean value of the westward electrojet magnitude, the red color shows the observation values, and the blue color shows our model prediction. So we can see that the prediction of the JY component tends to be underestimated compared to the prediction, compared to the observation, during these substorms. So why our model, our MSE for our loss function model has always underestimated from the prediction? So this is because the space physics data has a problem, which is well known as the imbalance data distribution. So here is a very simple and classical example for the imbalance data distribution. So in the image recognition task. So for example, if you imagine there's a photographer who just frequently take different photos in a city, right? So he or she can take tons of pictures or photos in the city, something like the houses, like the trees, or the museums, right? So different landscape, but a lot of data or images are the commonly distributed stuffs, something like trees and houses, because there's a lot of trees and houses in a city, right? But the museum, maybe in a museum, maybe in a city, in a single city, maybe there's only like the 10th museum in total, less than 100 at least in most of the cities, right? So because of this, the portion of the museum, the class, the class of the museum only occupy a majority of the total data sets, right? So basically, it's like a long tail distribution. So when we did use a machine learning model to predict the classification task to identify which picture is tree, which picture is houses. So our model usually can performs well. But when we use this model to classify which pictures is a museum, it may be not good. The performance may be not as good as we expected, because data set because the portion of the museum images only occupy a very little portion in the total data set, right? So it's the same.
Oh, looks like we've lost our speaker.
Yeah,
Just give it. Yeah.
so he'll be back.
See my screen?
Yes, we see your screen now.
Okay, cool. Thanks. So let's continue. So why our model prediction always gave us underestimation compared to the actual observation? This is because our model did not take account of the imbalanced distribution of the EIC data. So the EIC data is highly imbalanced because there are significantly more quiet time intervals than magnetospheric substorms or storms. So therefore, there are more small jy values than large values, which means the majority of the time consists of a relatively quiet ionospheric current pattern, and the active ionospheric current appear in the minority of the time. So such an imbalanced type distribution commonly exists in space physics and many other scientific data sets as well. So to overcome this imbalance issue, we need to customize the objective function or loss function to emphasize the minority of the data set and penalize the majority of the quiet time values, since they are of the relatively little interest to us, and so that the model learns better how EIC responds to its drivers during the active periods. So the left side describes the traditional MSE loss function, as you know, right? And the right side just shows you guys the focal loss function. So it's pretty simple to identify the difference between these two functions, right? So you just think about the MSE loss function as the L2 loss function and focal loss as a L4 loss function. The only difference is the power, the number of the power, right? So MSE is a power of 2 and focal loss is a power of 4. And because of this, you can simply think about the focal loss function is something like a weighted L2 MSE loss function, right? So because of this, if the observation, if the prediction do a bad work when compared to the observation, the weighted will make the loss function larger to pay more attention to the imbalanced part of the data sets. So right now, we have two prediction models with two different loss functions, right? So one is MSE model, focal loss model. So we can now show the results comparison between the two models. Here we show the model observation comparison for each model. It's obvious that the focal loss model, as the right-hand side shows, gave us a much better model prediction results compared to the MSE model, since the results of the focal loss model is much better to be aligned with the diagonal line, and there is a much weaker boundary cut for the large magnitude in the plot. And we can also look at the event analysis for the MSE loss function model and focal loss model. If you look at the Q-gram and U-gram, and you can find the JY magnitude of the focal loss model, which are the red color in the model panels, is higher than that of the MSE model, and also more close to the observations in magnitude, especially if you look at the last panels comparison, right? The last panel, the mean magnitude of the JY, you can find out that our focal loss model prediction matches pretty well with the observations as well, especially compared to the MSE loss function model. Right. And also, if we look at the second substorm event here, we can also find similar patterns. The difference of this event is that we observed two discrete enhancements. This is the first, the second, right? Enhancement. And for the EICJY during a single substorm. In this event, we can also figure out that compared to the model, our focal loss model gave us a much better prediction in magnitude, which matches the observations very well and successfully reconstructed the two discrete enhancements for the EICJY prediction. So here we demonstrated the comparison of the EICJY in geographic map between the observation, the MSE model, and the focal loss model, right? And we can see that compared to the observation, the MSE model is some kind of like underestimated in magnitude, right? And the focal loss model so improved a lot, right? So beyond the prediction in the EIC's observation region, which is limited to the North American and Canadian sector, our model can be also extended to make a global prediction, which is do some kind of like the extrapolation, something like that. So the first row shows the global prediction from our model, from our focal loss model at 4 different time steps during a substorm, which covers the whole range of the longitude in global. So, and then the second row shows the regional observations we have from the data set, which only covers the North American and Canadian sector. And the last row just shows the polar view of our global predictions. And this is another example to show not only for the substorm, but also for a geomagnetic storm. So the left side is a measurement for the upstream driver measurement. Right hand side is just show you like the animation of the compared to the prediction and the observation. So the first row is a global prediction, and the second row is the same as like the observations, regional observations as well. Yeah. So you can see is how the variation evolves during this geomagnetic, big geomagnetic storm, especially the peak values like the very blue color region and red color region. Yeah, let's go ahead. And besides the global prediction, our model can also make the long-term predictions as well. So here, we demonstrate the prediction results from our model that the comparison with the observations from 2007 to 2018, like more than across more than 11 years in total. So as you can see that our model prediction in the Q-gram and the U-gram like always matches pretty well with the long-term observations as well. So this shows us our focal loss optimized neural network model. So basically can do very well in the like the very short time prediction, like minutes time for the substorm events, and also for the big magnetic storm events as well. And also our model can extend it to from the original data set observation to a global prediction, and also our model can do a long-term prediction across like an entire solar cycle as well. So that is basically what I want to share with you, my recent machine learning for space physics work. And I will just leave it here for if you have any questions. Thank you.